This is a presentation that I put together for a friend's PowerPoint party with the intention of trying to cover the evolution of rocket engines from first principles to staged combustion in 3 minutes. It contains at least 2 deliberate errors, possibly more. Rockets are things that move forward by pushing stuff that used to be inside them backwards as fast as possible. By conservation of momentum, pushing stuff out of the back also pushes the rest of the rocket forwards. If you do the math on that, you get Tsiolkovsky's rocket equation, which tells us that how fast we can go depends on how fast we can push the stuff out the back, and also on how much stuff we can push out, and that's why rockets tend to be huge. One of the easiest things to push out the back of a rocket is gas. If you increase its pressure, it pushes itself out. A great way to increase the pressure of a gas is to heat it up, and a great way to heat up a gas is to use a flammable gas mixture and to set it on fire. For example, methane and oxygen do this really well. Because we want the exhaust gas to be as fast as possible, we want high pressure and light molecules in the exhaust because they go faster for the same pressure. So having some unburned stuff in the exhaust can actually make it faster, and that's part of why rocket exhausts are usually still on fire once they're outside the rocket and get more oxygen from the air. We can also make the exhaust faster by adding a nozzle, because when you blow gas through a smaller hole, that makes it go faster. We'll also add another nozzle outside this one that scoops the expanding gas to make it expand backwards instead of expanding outwards. To keep going faster, we need to keep putting gas in. If we put too much in all at once, it will burn very quickly at very high pressure in what rocket scientists call an explosion. So we keep the fuel and the oxidizer in separate tanks so that we can take a lot of it with us without it all going off at once. But gas is a pain to store because it takes up a lot of space. So instead we can use liquids. We can use liquid oxygen and liquid methane, and then we can get much more into much smaller tanks. They have to be kept really cold, otherwise they'll evaporate, but that's kind of okay because rockets use them up really fast, so they don't have much time to heat up. Great. But liquids can't supply their own pressure. We need pressure because we want high pressure in the combustion chamber, and in order to make the propellant flow, we need a higher pressure in the tanks to push the propellant into the combustion chamber. So we can keep some gas in small tanks so that we can let it into the main tank to keep the same high pressure. Great. Now the problem is, fire is hot, and using pure oxygen makes flame temperatures much hotter. So we'll run some cold fuel around the outside of the combustion chamber to stop it from melting. And this gets us a rocket engine that's almost good enough to get to space. So what do we need to do to get to space? We need to increase the pressure of the combustion chamber, so we need to increase the pressure going into the chamber. We don't want to increase pressure in the tanks though, because that'll need to make them heavy. So instead we'll add a pump to push the propellant into the chamber at super high pressure. That's great, but how do we power the pump? It needs a lot of power. We can use a gas turbine and burn a wee bit of the propellant to generate the gas that spins the turbine that powers the pump. But yet again, fire is hot, so we have to chuck in a lot of extra fuel just to make the flame temperature lower. This is the cycle that the first stage engines on Saturn V used, so it's good enough to get to space. It has lots of thrust, but it's not very efficient because there's a lot of unburned fuel in the turbine exhaust that we could have burned to go faster. So let's run all the fuel through the gas generator and then into the combustion chamber. This is called fuel-rich staged combustion. First, all the fuel is burned with just a little oxidizer, making it into a hot gas, but not too hot. That hot gas spins the turbine and then burns the rest of the way when it's added to the rest of the oxidizer. But more stuff going past the turbine would make it cooler and also more efficient, so we could make it smaller. Since on most rockets there's more oxidizer than there is fuel, we can use the oxidizer instead. That's called oxidizer-rich staged combustion. This is the cycle used in the RD-180, which is the Russian engine that's so good that the US is still buying them from Russia to launch spy satellites to spy on Russia with. But what if we could use all of both the fuel and the oxidizer? So let's combine those and we get full flow staged combustion. There's 2 pre-burners and 2 turbines now, but they can be less than half the size since they can run cooler and work with denser gas. Also, we now have completely separate fuel and oxidizer systems, which means that we don't have to worry about sealing the pump shafts so well. Both propellants are already gases when they enter the chamber, so they mix more efficiently and more quickly, and the main combustion is faster and more efficient too. So it's high thrust, small and light, and very efficient. And the only one of these that's ever made it to production is SpaceX's new Raptor engine, which makes it really exciting despite the fact that Elon is kind of a twat. Anyway, pretty simple really. I mean, it's not exactly brain surgery, is it?